Okay, now that we have the basics of waves understood, let's start talking about different kinds of waves, specifically those related to light and sound. So the wave we've been talking about so far is the transverse wave, which is a wave that vibrates up and down, but travels sideways, so perpendicular to that vibration. Okay? So the vibration is up and down, and the wave travel is sideways, so that is a perpendicular relationship between those. If I draw the equilibrium line, it's easy to see your amplitudes, your crests, your wavelengths. Okay? And this wave is the one you should be familiar with. What I want you to make sure you write down is that a transverse wave, examples of that come from light. Okay? A light wave, which includes radio and x-rays and what we can actually see, is the main example of a transverse wave. Now, longitudinal waves we have not talked about before, and they have some similarities and some differences with transverse waves, but the main difference is that the vibration direction is parallel to the wave travel. Okay, so if you think about a slinky, if you've ever taken one and just kind of pushed it backwards and forwards, and then it kind of creates these compressions as it goes through, that's a longitudinal wave. So to make the wave that's drawn down here, the hand pushes backwards and forwards, and that creates compressions, and expansion's not actually the right word, rarefactions. Okay? And then you can have similar terms related to our transverse wave. You can measure a wavelength, say from the middle of a rarefaction to the middle of another rarefaction, okay, or from the middle of a compression to the middle of another compression. And then there's no amplitude because it doesn't go up and down. And then the words crest and trough are replaced by compressions, which are the areas where it's really tight together, and then rarefactions, which are the areas that are kind of spread out. And then the main example of this is sound. Sound is a wave that is longitudinal. So some similarities that sound and light waves or transverse and longitudinal waves have in common. One, they're both waves. Both types of waves have periods, frequencies, wavelengths. And cross that one out. They don't both have amplitude. The compressions can pass by in a certain amount of time, well, just like the crest can pass by in a certain amount of time. Or you can get a certain number of compression and refractions, so whole longitudinal waves to go by per second, just like you can get a certain number of up and down crests and troughs to pass in a second. Okay? They both travel at a constant velocity. And we'll talk more about that on another slide. So in general, they move at a constant velocity, though they do move at different constant velocities. They both obey the wave velocity equation. Velocity is always equal to the wavelength times the frequency. And then they both experience reflection, which means they can bounce off of things. Right? The reason you can see yourself in the mirror is because light is bouncing off of the mirror and coming back into your eyes and making a picture of you. And reflection of a sound wave makes an echo in a cave or a tunnel. Okay. Some of the key differences between sound and light, one is their type of wave. Sound is longitudinal, light is transverse. And then requirement of a medium to travel through. Sound waves have to have molecules to compress in order to create that wave. If there's nothing there to be compressed, like in a vacuum in outer space, sound waves can't be made. Whereas light waves, the transverse waves, don't require any medium. They can travel through a vacuum, they can travel through anything. Okay? And then the speed, while they both move at constant speeds, sound moves much slower. It's at 343 meters per second. You might see a range of velocities for sound because temperature does make a slight difference. So you might see between like 340 and 345. And then light moves at an incredibly fast rate of 3 times 10 to the 8th meters per second, which is a 3 with 8 zeros following it. Okay. Another big difference between sound and light is how we perceive it. Okay? The compressions create, when our ear gets the sound wave, the compressions create a frequency that, it vibrates our ear bones and our eardrum, all right? And depending on what that frequency is, we hear different pitches, okay? So low pitches, high pitches, and we'll talk about that a little bit more. With light, when it comes into our eyes, the different frequencies of light actually give us different colors, okay? Blue is a different frequency than red. But we'll talk about that a little bit more too. Okay, so when hearing sound, all right, the ear recognizes those compressions, and those create the frequencies that the ear can recognize, okay? So depending on how quickly the compressions come through, more compressions equals a higher frequency, okay? So the more compressions the ear interprets, the higher the frequency of the sound the ear interprets. Okay? Now, humans don't hear every single possible frequency of a longitudinal wave. For most people, there's a range of 20 to 20,000 hertz that can be heard. And then 20 is a low pitch. Okay? The low frequency, and hertz is the 20,000 is the high end, or the higher pitches that we can hear. All right. Now, frequencies that are lower than 20 hertz that we can't hear are called infrasonic. Okay, so below hearing level. That's what the infra means. And then frequencies that are above 20,000 hertz that are too high for humans to hear are called ultrasonic or above hearing level. Okay, so sonic implies sound, and then the infra means below and the ultra means above. Okay? All right, so human perception of light, we usually refer to the different colors as different wavelengths. They just did not use the same terminology as they did with sound, but the same thing, similar words apply. So there's a certain range of wavelengths which also correspond to specific frequencies, since if speed is constant, okay, since the velocity of light is always the same number, as wavelength goes up, frequency must come down, okay? So the highest wavelengths are in the red range, which means these are the lowest frequencies. Low frequency. And then the shortest wavelengths, 400 nanometers, purple and violet, so since those are the smallest wavelengths, those are going to be the highest frequencies that we can see. Okay? And they have similar terminology to the sounds, all right? Any wavelength or frequency lower than the red range is called infrared, okay? So that's below red. And then any frequency higher than the violet range is called ultraviolet or above violet. Alright, so I would, in a general idea, know the ranges. You don't need to know the specific numbers per se for light. Just know that we can see from violet being the high range in frequency and red being the low range in frequency. And then don't forget to do the online form, and I will see you in class.